except that now what I'll try to do is that go into some of the challenges actually. And there are far too many challenges, so I won't be able to cover all of them in the 25 minutes. I may rush through some of them, but more than that, what I've tried to do is that try to put as many as I can on these pages and not go through details, and that's again something that we'll be doing over the discussions. So this is the outline, overview of some of the surveys and data holdings that we have, various data types that we have. By data types, I mean not the Python-like data types, but just how the kinds of holdings that we have. And I see Matthew mumbling that maybe he's going to say some of these things, but there are going to be commonalities all over. Variability searches, and that's, I think, where if one is looking for variability, only a small fraction of objects, astronomical objects, are variables, and if one wants to find them early, how can one go about doing that? And different people use different things. We have found that something like Stetson J is useful, but then you cannot use it as a single parameter over the entire data set and so on. So coming to use specific data sets, specific techniques, but then being able to combine them in a homogeneous fashion is something that's going to be a big challenge, especially when we have very large data sets. And period finding is another thing. If you have got a very good data set, if you have got a very good time series, then period finding is not too difficult, but most of the times we are not in that regime, so we need to be able to find periods even when the data are horrible. But we should be able to do as best as we can and go on from there. So how to go about doing that? Combining surveys is another crucial thing. Again, as I said before, most surveys have specific aim, and then that aim defines how the survey happens. And yet when there are multiple surveys, there are ways of combining the data sets. And that is a powerful way of using all those data sets together. And how can we go about doing that? And combining classifiers. There are a large number of classifiers. Rather than let them work on their own, how can one try to combine them in meaningful ways? So snapshot of the surveys that we have. Here is CRTS, for instance, which has been observing for more than 14 years, most of the sky, both in the northern hemisphere and the southern hemisphere. It doesn't use filters. PTF, for the last several years, it has been covering large part of the north sky. Gaia started observing a couple of years back. It's going to have fewer number of observations, only about 70 in 5 years, but it has low resolution spectra, and of course the astrometry is going to be fantastic. So as you can see, the types of data that these surveys get are very different from each other, and we should be able to find good ways of combining them. And of course, as I mentioned in the previous week discussion, LSST, which will be coming on, it's going to have, it's one of the main things that it'll be doing is that it'll go very deep, and it'll have a large number of objects that it'll be observing. So how to be able to classify that at the rate at which LSST will be finding things is going to be a challenge. So what is it that surveys do actually? Most of the times they're after low-hanging fruit. They're designed for specific things. They're going after that. They try to select the best objects that they have, and I have called it easy science. It's not really easy. I'm just trying to be overreaching in terms of saying about the low-hanging fruit. So they define something, and when you define it, if you do the survey well, then that science becomes easy. But much of the rest of the science still stays hard, and being able to get to that. So again, many surveys then do a little bit of spectroscopic follow-up. This is great. You get to know what those specific kinds of objects are, and that does push the envelope, but also it leaves a large number of gaps because you cannot do spectroscopy for more than a few objects. It's a very expensive thing compared to imaging and most of the other data that we get. So that is something that we'd like to get away with, and one way to do that is through machine learning, statistics, and so on. So with LSST, what we're going to have is that there are going to be 1,000 observations each 30 seconds. So that seems a lot, but it's over 10 years. And if you have the 10-year timeline along this room, for instance, which is about 10 meters, then only 1 millimeter of that will be actually covered by the observations. So 1,000 times 30 seconds over 10 years is going to be a really small fraction of time that we'll be looking at any given object. And that's the kind of that data that we'll have in order to try to classify that. Today's holdings again, so with CRTS we have several 100 million light curves, and there are 1 billion cutouts. These are being served from IUCAA right now, so almost all the data are public here. With PTF, which is partly public, there have been some data releases. It's multi-filter, unlike open. And the CRTS cadence is designed for asteroids, so it's lumpy, so you take 4 images within 30 minutes, and then don't take another set of observations for maybe a week sometimes. So it becomes very chunky, lumpy that way. Then there are various data sets like for streaks from nearby asteroids with PTF, with Pan-STARRS and Gaia. These are again multi-filter, and there have been small data releases. Over the next few years, we'll see more. But with Kepler, it's very interesting. It's a very small area, but these time series are very non-sparse. So they're ideal if you want to start designing some algorithms, which then you may want to go on to sparser time series. So you have a very good labeled data set that you can get. But again, because the area is small, then you do not have very large number of objects there. And then we'll hear a little bit more about pulsar timing arrays in this workshop too. We are not going to go into exoplanets here. That's what Kepler does a lot with. So there's a whole set of methodology with those that is out there. And then again, quick properties for light curves that we have. This is of course a very extreme light curve, but in general, the time series that we have are very gappy. There are huge gaps, as I mentioned. They're very irregular. So if you're looking at financial time series, then you can do many, many things really well, because every morning the market opens, and then you have got observations, and then it closes, and then it again opens, and so on. Not so with astronomy data. So you cannot use data or techniques directly from any of those other things. And then again, the error bars tend to differ for various reasons, including the atmosphere itself. So all those issues make the time series that we have in astronomy likable by many statisticians. They love the data because they present new challenges, and some of those challenges are what we'll be looking for here. And errors are ignored by many methods as well. So trying to bring those in, trying to have more methods use errors will be a great thing. And again, the sparsity of the time series. So you don't have to read the axis here, but this is several years worth of data and a few points in each year. But compared to that, the Kepler time series from a very small fraction of that time period, and you have got a very large number of points. So these ones you'll want to try to combine. And the interesting thing is that if you look at a single light curve, if you look at a small portion for the same object, then depending on where you are looking at it, it can look very different. And so if you are getting features, statistical features from those, then they're going to look very, very different. And that's the kind of thing that one is trying to look at. So not very different from the elephant and the blind people trying to see what the elephant is. So our time series are in a way like that. Right, meaning for that particular outburst, the dwarf nova, it is, so what combinations we have. So there is, in fact, a subgroup on light curve decomposition. So when you see a light curve, you can have various things contributing to that. And if you're looking at only a section, maybe that particular phenomena is more active, and that's what you're seeing at the time.
Previous slide, what were the different points?
Okay, sorry, yeah. So each of these points is an observation, and you see the error bars there, and the ones that are in red are upper limits. So at that time we were looking in that direction, but we did not see that object. And then by knowing what aperture we have, we can say that if it was, the object must have been there because we see it over a long time. So what is the brightest that it was? We can say that, and then the line indicates that. No, same instrument. It's by the same instrument, yeah. This is a homogeneous light curve. This is from CRTS, so no filter open. And then.
How can there be upper limit and rejection?
No, not at the same time. But as I said again, with CRTS, we have got 4 observations within 30 minutes. So it may happen that you see it now, but 10 minutes later you don't see it. So that's the kind of variations that you can have because it's a variable or because it's a transient. Rarely you can have asteroids passing through, but in this particular case, because of the large number of detections, we know that it was a static object. So. And then the upper limits are different at different times, again, because of atmosphere, for instance. Right? And so one of the things that has happened for the last several years is that given a time series, you get various features, you derive various statistical features and try to use those statistical features for clustering, classification, and so on. So Richards et al. Had this paper where they used non-sparse Ogle and Hipparchus time series data, and they defined a bunch of things, simple things like amplitude, what's the difference between the magnitude and the minimum, then you could divide it by 2, for instance, and so on. So that is one of the features that simply tells you how variable that object is likely to be, because most objects that we see, more than 90% of the objects are not variable to the extent of small telescope observations. Of course, there are always small variations that you see in all objects, or then beyond one standard deviation. So if you just get the standard deviation for your time series, what fraction of your points in the time series are beyond that? That tells you how many times an object is varying. For instance, a supernova will typically have a very big, broad peak, and then it'll fade away as the dying star stops. Its light stops reaching us in a big way. Or if you have got flaring stars, then you will have objects that become brighter in a short amount of interval, and then it fades quickly. There are other things like cataclysmic variables or AGNs, which have variations more number of times, sometimes at lower levels, so stochastic essentially. And all those things can then be, one can try to capture them by defining a large number of such variables, and we'll be seeing more about that later on. So here is a whole set, and there is a service that we have. It's not a huge service, so if you want only a few light curves for which you need those observations, you can get those from here, for instance. And if you look at how these statistical features look, then and plot them on top of a single light curve, you can see that they are trying to get different aspects of the time series in different ways. This, what's shown here, is a phased time series. So one has already found out the period and folded it on top of that, and so on. So for instance, beyond one standard deviation or maximum slope, so you could have, take every 2 successive points and see what is the slope between them, and ask that for any given object, what is the maximum slope for that. So there are tens of such things that are defined, and of course, unless you have that many points, then it's not meaningful to have that many dimensions from your data set. Or the other thing that happens is that if you have a very large number of points and most of them are upper limits, then you won't be able to get to some of those features, and so on. So those are some of the challenges. And so as I mentioned before, Stetson J, I was singling it out because we have used that for variability before, and there are various things that have been defined for something like that. So how it started is that this parameter I was defined where pairwise observations in 2 filters were used. So you have got the B filter and the V filter, so you take mean in B and mean in V and find out how the residuals are with that, and you define this I, which was used for variability. But then if you did not have 2 filters, how to go about using a single filter to do that, like we have in CRTS. So you can simply use pairwise observations within a single filter and define a similar thing, and that is what the Stetson J statistics is. So you can define the residuals and do it. And then if you want to say that I don't want to go after pairs, because finally I have a time series, and pairs, you are restricting somehow what you can infer from the time series, then you can use it without pairing by finding out how many points you have and redefining your feature. Here, for instance, K, if it's a Gaussian kind of process, then you get this specific number 0.798, and then you get different numbers for K depending on what kind of time series you have. And typically, so what happens is that you don't use K as it is, but use K divided by 0.798, so that you are in some sense normalizing, and you can define L, which can be used for thresholding and so on. So there are these various things that people have defined, and they use it for specific use. And then those features have been handed down, and then all those things come about. But again, one main thing is that the features are not independent of each other. And if we continue to use them en masse, then we are going to have a large number of things that may or may not make sense for the particular kind of time series that you have. So disambiguating those is an important thing, and given your kind of time series, how to get to specific features becomes important. With CRTS, we did a set with 150 million sources. It turned out that there were 5.5 million variables among those, and 50K of those were periodic sources, and there were about 15 classes within those 50,000. We've been doing a lot of experiments with that, so this week we'll have more time to talk about those, because that data set is out there public, and we can torture it in many different ways. Other people have defined other things. This Q is an amplitude variations. This is from Cody et al., where you take the RMS for the raw time series and use it along with the residuals after you have subtracted out your phased time series. And then based on that, if you have a fairly uniform version, you get Q equal to 0.0, whereas if you have very non-uniform one, it tends towards Q 1.0. So this is one of the features that can be used. Another one is where what you do is that you find out points that are either in the top 10% or the bottom 10% and compare that with the median for the entire time series, and you define this M with that, which gives you bursters and dippers. So here again, minus 0.53 is what you get for something that is very irregular with a few bursts, whereas here there are more variations, 0.25. Here you have got more dips, so it goes to a larger positive number. And then when you use Q and M together, you get something like a QM plane, which starts separating some kinds of objects. Again, for specific kinds of objects, this can be a very good thing, but how to combine that with something, with all the other features becomes an important, interesting problem. So Matthew here has worked on this, where you use RL array and eclipsing binaries. How can you use a very small number of features to try to separate those? Again, if you can find out those 2 or 3 specific features, then separating these 2 classes becomes easy. If not, you go for a toss, and their typical distributions overlap with each other. And so in all these, what we find is that the kinds of features that we have is huge. And some of them, for instance, come simply from discovery. They're magnitudes or delta magnitudes. Some of them are contextual. What is the nearest star? That tells you something about the nature of the object, if it's likely to be. If there is a galaxy nearby, more likely it's a supernova if you're looking at a transient. If there is a radio source nearby, it's more likely to be a blazar, and so on. Then when you do follow-up, you get certain colors, so those become important features. There are prior classifications, event types, those become useful. Characteristics from light curves that we were saying, and then various different measures which you can define either on the whole curves, or you fit them and get residuals, so you can define something new on residuals, so those become important and interesting as well. So choosing from these becomes an important thing. And of course, then there are these various methods where you can try to say which of these features are more important than the others. So you can define the importance or the significance for each of these features. But again, for these, what is important to ask the specific question, for which classes are you asking it? If you're asking it for an entire survey, the answers that you are going to get are going to be different from when you're choosing 2 specific classes. So again, that issue is there, how to try to go, say, in binary classification mode, or a hierarchical classification mode, or a homogeneous classification mode, and so on. So here, for instance, what this is showing is that these top features are more important than the ones that are here when you come to, so the dimensionality that you have finally is not the 50 or the 100, same as the features that you have, but the feature dimensions, the real dimensionality is, say, 3, 4, 5, maybe up to 10, and so on, and coming down to those is going to be important. So the x-axis simply says their importance. It's a relative fraction that you're getting. So how this top thing is able to distinguish between the 2 things that you are trying to distinguish. And so this says that the lowest one, it does not have any discriminative properties at all.
You say that one component would discriminate 70%?
To an extent, yes.
I think this and also the Q dimensional is not just these things. The question will be, how will these things carry over the
Exactly. So that is what I alluded to in a very different way. So some of these features were developed for non-sparse time series. And if you get to sparse time series, you suddenly find that there is far more overlap when you look at those. So they become less useful. And when you go to less signal to noise, exactly the same thing is likely to happen. And so defining those boundaries becomes important. And when can you use a particular thing, when you cannot use a particular thing? Or are there variations that you can define for those which become useful for lower signal to noise? That is where I think the statistical framework can become useful. And so one of the challenges is choosing judiciously what we can get into. So this is how the picture used to be long back several years ago when NVO was around. So you had a few event parameters and you got event classification engine. and then you had some prior information that you fed in and some contextual information. And what you wanted was not hard classification, but soft classification, where you could attach probabilities to all different classes. You don't want to say that this is this for sure, but you can say that this 99.999%, but maybe 0.001% is these classes also, which you can then update based on the new information that you can get. And so that feedback is very important. And now things are changing with LSST and so on. Again, what's going to happen is that the data stream is going to be much larger. So the same picture looks like this now, with all those things coming. Conceptually, it's exactly identical to what we have here, but there are more bells and whistles that you need to put in. And so the rates for LSST are going to be about 1 to 10 million transients every night. And by the end of the night, what we expect to find are about 1,000 rare transients after having gone through all these things. I'm not going to go into all those details. So this is from a prototype broker for LSST that NOAO is building called Antares. And LSST images are going to be far deeper, and there are going to be more filters, but they're going to be equally sparse compared to some of the things that we are looking at right now. And so characterizing rare transients quickly with minimal data is one of these challenges. And then periodicity, I won't go into details of these, but we know that Lomskargil method has been used for a long time to get to periodicity. And we have been looking at various entropy-based periods. Again, Matthew has a paper on that from some time back. So if you simply count the K partitions that you have for your time series, and you have to bear in mind that there can be one-day aliasing kind of effects that you get, because that's how astronomers like to observe things, try to observe things that are close to zenith, because you get more signal to noise there. So keep that in mind. But it's the K partitions that you look at after phasing that gives you the most likely period. But then you can also go to 2 dimensions. That's where the entropy comes in. So you partition not only in time, but also in magnitude, and find out what is the most likely period that you get from there. But one of the challenges is better period finding algorithms with sparse time series. Then there are a large number of classification and clustering methods, both supervised and unsupervised. So you got support vector machines, self-organizing maps, and spanning trees and distant trees. So random forest, one thing that happens with random forest these days is that if any method can beat random forest, then it is a good method, because random forests generically have become very, very good of late. But of course, they can be beaten for specific classes, and finding out what those classes are is important. Naive Bayes, for instance, is very good. If we can use fully Bayesian distribution, fully Bayesian analysis, that's fantastic. But the dimensionality is so large, typically, is that there is no time. The computation that is required for those is very, very large. It goes to very large powers of 10 very quickly as the dimensions increase. So one way to do that is break down the big problem into smaller naive Bayesian problems. Like here, for instance, one can try to separate supernovae from non-supernovae using just 3 features, none of which requires follow-up observations. So if one can do that for every pair of classes in a hierarchical fashion, then that will be fantastic. But again, identifying how you can do that is a crucial thing. So here what we are using is normalized distance to the nearest galaxy. There can be more than one galaxy nearby, nearest distance to a star, and a prior outburst statistics that can be defined by seeing how the peaks are distributed and what is the area in time that each of that peak covers. And so designing specific feature, domain knowledge assisted features is an important challenge that we have. And meta-classification, trying to combine all these classifiers, some of them probabilistic, some not probabilistic, is a big, big challenge. Because again, in silos, there are many methods that exist, they do well. But if you want to do everything for everything, then how to combine them efficiently is a big challenge. Another thing that's going to be important is how do you combine different data sets. So CRTS, PTF kind of data sets are in between here. They go deep enough, but not as deep as some of the surveys that will come about. The sparsity is there. And then there are surveys, not surveys, but compendiums like DASH, which looked at a large number of photographic plates going over 100 years, only to bright limits. So we have got a very good history there. And here, of course, only 2 dimensions have been shown, the year of observation and what the brightness is, but there are all kinds of other things based on apertures, filters, and so on, try to combine those. So there are methods like domain adaptation, which can try to combine these different data sets, even when they have different cadences, different filters, and so on, where one what one tries to do is that do learning from one survey and a little bit of another survey so that you can start predicting what you are likely to find with the second survey with very little data sets. So that's going to become more and more important as we start combining these data sets. So here is how, for instance, how features look. So we took those 50,000 variables that I mentioned earlier, the periodic variables, took light curves from PTF and CRTS for the exact same set of objects and derived the same statistical features for them. Again, you don't need to read what those features are, but these are the features that we had for the time series before. And when we look at PTF versus PTF features, then of course there is a correlation along the diagonal. But for the same set of objects, the same features, when we compare PTF versus CRTS, we don't see correlations, and that's because the two surveys are very different from each other. And yet we want to use the two data sets together, and how to go about doing that, that's what the domain adaptation allows you to do. Sorry? They will be somewhat different from each other. The diagonals are simply saying that correlation between one value and the same value, right? Meaning. Right.
I see some similarities also.
Yeah, the similarities
with the top. Right.
So they will be identical, right? Meaning the PTF versus CRTS and CRTS versus PTF. So you'll have those identical in some sense. Okay, yeah, we'll talk about that. It's in some cases it may be simply small number statistics and rounding off that comes about. So here what's happening is that for the same set of objects you get different planes, and it is how to go about orienting the two planes so that you can combine the data sets is what one is trying to get at. So this was the 50,000 variable set that I mentioned, and this is how the codomain adaptation looks. So I should be skipping that. And so I have not covered many of the challenges, of course, which will come about in this week later on, where light curve decomposition and data challenge and outlier detection and so on. So I'll leave you with the summary of challenges. So what we are trying to get to is that characterize and classify as much with as little data as possible. That's going to be really the aim that we have. Only a small fraction are going to be rare, and finding them quickly and characterizing them early is going to be crucial. There are a huge number of parameters, and choosing out of those for your specific science is going to be very important. Real-time computation is required, and finding ways to make that happen, make computation faster, be able to have workflows that allow that to happen, and meta-classification, combining diverse classifiers optimally. I'll stop with that. Thank you, and we'll keep on discussing these, of course.
I had two questions. One was, what is thought of in terms of getting into the digital domain, the archival data, because some of the science questions that we would like to address can be better addressed if we have long timeline data, and the only way to do that is to go back into the archives, and it might involve even non-digitized data, photographic plates, all of that. So what has been the what is the state of the art on that was one question. And the second question was, now all these various methods have been used for a few years already in collaboration with the statistics academia. So in terms of, which method is good for what purpose, and, do you use KAS, or do you work in the Fourier domain, or whatever? Is there some sort of evaluation of all these different methods so that a fresh a person can have access to a comparison, before trying to.
So many times what happens is that, okay, let me answer your first question first. So this DASH that I mentioned, they have been digitizing photographic plates, and they have data for over 100 years. Not all of it is public, a fraction of that is public, but their aim, they are funded by NSF to make all of it is. China has been doing a lot of digitization for their own plates, but I haven't seen any public data from there. But I think these organizations will be interested in digitizing more sets, but if there is an organization here in India, for instance, where old plates could be used, that will be great. But there are efforts already underway, and a fraction of that is public. And then surveys like CRTS have large public archives, and then other surveys that I mentioned, PDF, Panstras, Gaia, they have been releasing data that's public. And the VO-like methods are quite good to try to get to all of them. Again, there is no single store where you can access everything yet, but you can still get a large number of these. And I think Rafael may be mentioning some of these in terms of data challenges about different sets that are available right now and so on. Then the other question was about using common methods for different sets. And that's one of the things that, there are two things. One is of sociology, where if you belong to a particular survey, you tend to keep talking about that same survey, of the methods that you keep on using. And when other people try to use that, they sometimes work, they sometimes don't, and that may be because of the characteristics of the survey that are different, characteristics of the data set that are different. And that is the thing that I was mentioning about combining data sets, one of the challenges that we do have. So we do have good lists of things that are available, and when they don't work, not to a very great way, but quantifying that will be one good way. And so again, going to something like lower signal to noise or sparser time series. So having a good description of that in a single place will be of great utility.
Yes, Ashish, I had two questions. One was, one was about, you had shown that data where it is quite gappy. So within one block where you have the observations, what's the typical duration duration of in days?
So sorry, what was the first part of the question?
So the data, the light curve was quite gappy when you showed them. So within one block where you actually have observation, and then there's a gap, right?
Right.
So within the block, what is the typical duration of observation?
Okay, so that's going to differ from survey to survey. So I think the one
CRTS, let's say.
for CRTS, what we have is that in 30 minutes there are 4 observations.
Okay, so
and the next set of 4 observations may come the next night, or sometimes the same night, or a week later, or sometimes even a month later.
The median value.
10 days. Okay, so
so what I'm asking is that looks like a few days when I look at it. A 1 bar.
This is several years, right? This 3,000 days.
Yeah.
So this whole cluster is 1 year.
Okay.
And so we have a few observations within a year. So the total number of observations is a few hundred typically, or several years.
Okay. So has someone looked at the second question, the last one? Has someone looked at transients which are not burst type, but say not non-repeating and last for a very short time?
Right.
And have someone looked at that kind of transients, and do they appear in some part of that 2-parameter plane that you showed?
Yeah, so we have been looking at some of that, and not all of it is published yet. And then we have a corresponding catalog called the Orphan Cat, at which we have been looking at, where we do not see objects over the several years, but over only a small period, and what one can do with those. There can be many artifacts within that, of course, so one has to be a bit wary about that. But yes, something has been happening, and we can talk more about that because that's not been fully explored yet.
So has there been any attempt to leverage VO to sort of construct what we may call a light curve assembler? I mean, given an object coordinate, it goes and searches all VO archives and tries to give you a good time series with necessary flags about what may be an outlier and may not really be a cross match.
So there have been some attempts at that, and what NED tries to say, for instance, is that they try to put together an SED of an object, which is something like that. But what I have been trying to emphasize that what we need is a 3D SED, where you not only have energy but also have time, because same object in the same band has been observed multiple times, and there is no good tool right now for something like that. And
This talk. Thanks, Ashish.